Let's continue with tutorial 5, question 1 VII, where we are asked to find the output yn for different x. The first is x1n equals to the unit step n. So remember, we are only given the impulse response of the system. So how should we proceed? Basically, you should think of it this way. You have x1, which is unit step. So this is the unit step. All the values are 1 here after n equals to 0. This is being sent into the LTI system, where the LTI system has the impulse response. This find the impulse response when n equals to 0 is 1, n equals to 1 is 2, n equals to 2 is 1.25, and 0 is hence. So basically, y1 of n is x1 of n convolved with h of n. And then we can solve it this way. And of course, in MATLAB, you basically write filter b, a, and then the unit step is 1, 1, 1. Of course, the infinite value of 1, and then you get the output. So let's try with this first. So remember, b is equals to 1, 2, and 1.25, and a was 1. And then of course now this is x, and let us see what is the value of y1n. So first I enter what is the b value, I enter what is the a value, I type using filter b, a, and of course I cannot write an infinite unit step, so I just use a couple of values and out pops the output. So it is 1, 3, 4.25, and keep on staying at 4.25. So in fact, you realize that if I increase my x, it doesn't matter because it keeps on being 4.25. So the steady state response of this system is 4.25. And these two values here before is the transient condition. So by using filter, and basically this is simulating this, we get this response, and I should put n equals to 0 here. And here is the steady state, and here is the transient condition, or the transient response. Now if you're wondering how can we get this through the z transform, basically you should try this. Y of z equals to x of z, h of z, and then you'll get the expression. You should basically write the z transform of the unit step, which is 1 over 1 minus z minus 1, the z transform of h of z, which was what we had just now, and then you calculate this polynomial of z minus 1, which is quite hard to find, and then you basically do inverse z transform of y of z to get y of n, and you realize that this will pop up. So by using the z transform, we get the transient condition as well as a steady state. But in this question, we are only asked to find the steady state, so there's an easier way to do this. I'll erase this board here now, and I'll show you the steady state response. The idea is to observe that un is basically can be considered as cosine omega n, where omega equals to 0 radian per sample. And isn't this also just a cosine that is an infinite cosine from 0, 1, 2, and minus 1, minus 2. And of course, then you'll be thinking that our unit step starts from time 0, and it is, what do you call that, 0 before that. So although this cosine is representing correctly from time n equals to 0 to infinite, it is not represented correctly before time 0. But let's proceed, because when we study this as a steady state, we are assuming that actually we are sending all these values before time 0. That's the key idea. Right, we now realize that the frequency for un is actually omega equals to 0. So what should we do is that we want to find h of ej omega, where omega is equals to 0. This is the frequency response of the system. And how do we get h ej omega from h of z? It is simply substituting z is equals to 1 ej omega equals to 0 here. So you realize that there's a very close relationship from the transfer function, which is h of z, to the frequency response, which is h ej omega. In fact, what you realize is that the frequency response is nothing but h of z. This is the surface of z, and this is the unit circle, and we are evaluating z at this unit circle. So where do you think omega equals to 0 is? It is actually at this point here. This is the real part of z, and this is the imaginary part of z, and this is at 1 plus j0, and then this is j, this is minus 1, and this is minus j. So at 1 ej omega equals to 0, it is basically at this point. So when omega goes from 0 to 2 pi, we are actually following this curve, which is a unit circle from angle 0 to angle 2 pi. Alright, so we will evaluate h of z at this unit circle value. Now let's try. So we're saying h of z equals to 1 ej 0. So when we substitute this into our h of z, let's see what we get. First, let's write down h of z first, which is this polynomial of z minus 1. Now we substitute z is 1 ej 0. So it is 1 plus 2, 1 ej 0 plus the power of minus 1, 1.25, 1 ej 0 to the power of minus 2. Okay? You realize this is very simple. 1 ej 0 is 1. 1 over 1 is 1. 1 ej 0 is still 1. 1 over square root of 2 is 1 over square root of 2 is still 1. So basically it's 1 plus 2 plus 1.25, and the answer is 4.25. So you realize that there's a 4.25 here, and this 4.25 looks like this 4.25 here. In fact, it is. So what frequency response does is basically, to get the output, basically you substitute h of ej omega at a particular frequency that you want. In this case, omega equals to 0, for omega equals to 0 as a cosine, and then you just expand this h ej omega to get the magnitude and the phase. In this case, there's only the magnitude, so it is 4.25 times cosine of omega n, which is nothing but 4.25 of all at once. And in fact, therefore, y of n is equals to 4.25 for all n. And therefore, this shows us the steady state response. So remember that frequency response ignore the transient response, only give you the steady state response. So in this figure, we show you 3 different ways to calculate y1 of n for x1 of n equals to un. Thank you.